acids and bases relate directly to the solutions unit because acids and bases, by rule, need to be dissolved in water for them to work. So there's something about their properties that when they become solutions, that is what makes them an acid or a base. And some of the things that you're going to remember is the pH scale. You learn that less than 7 is an acid, more than 7 is a base, but you don't probably know what the pH scale actually means. Some of the other things that you do need to know about acids and bases are pretty basic properties. For example, acids taste sour. Okay, if you think of like lemon juice, vinegar, or that kind of stuff. Bases taste bitter. And the only other quality that you need to know is that bases also have a texture which is slippery. Okay, if you've ever, done cleaning with bleach or ammonia, or, obviously you've used hand soap before, those always leave sort of a slimy, slippery texture on your hands until you can wash it all away. So, working our way towards what this pH business means, the first thing that we need to know is what is self-ionization. So if we're looking at pure water, which we know is a neutral substance in the middle of the pH scale, it's not an acid or a base. The reason it's not an acid or a base is because two water molecules sometimes react with each other. And what happens is one hydrogen from one water gets stuck on the other one. Actually, I should draw this going the other way because that's how I did it over there. Let me just turn that around. Here, we'll take a hydrogen from here and stick it on there. So what you can see on the other side of these reaction arrows is we have now what used to be a water that has an extra hydrogen on it, and we now have what used to be a water that does not have two hydrogens. So this molecule we have done work with before. This is called hydroxide, okay, and this is the base molecule. So if you have a solution that has extra hydroxide in it, that is considered a base. Okay, meanwhile, the other thing is called hydronium. Okay, so this is water with an extra positive, and this is what makes a solution an acid. So the reason why water is neutral is because it's always making both things at the same time. So every time it makes one hydronium, it makes another hydroxide, and it cancels itself out. If you add something to water that only increases the amount of hydronium, you're going to end up with an acidic solution. If you add something to water that only increases the amount of hydroxide, you're going to end up with a basic solution. One of the misconceptions that Chemistry 1 students have is that acids are worse. Okay, but that is not true. If we go back to this scale, okay, if you swallow bleach, you're going to have a bad day. Like bleach and lye and other bases that are really, really strong, like Drano. Okay, surely if you've ever smelled Drano before, you can tell just by the smell that it's pretty nasty stuff. Bases are just as bad, just as toxic, just as strong as acids. It's just that they have the opposite charge. So bases have extra negatives, whereas acids have extra positive hydrogen. Okay, so when we say that something is a strong acid or strong base, that actually does not have anything to do with the pH scale. Okay, typically, if it is strong, it does tend to have a very low pH, like 1 or 2. And if it's a strong base, then it's going to have like a 13 or 14. But that's only a coincidence. Okay, the real definition of what strength means is that they completely ionize. So, let's talk about electrolytes. Okay, salt is a molecule, we've talked about it a dozen times now. When it dissolves in water, it makes positive and negative charge. Okay, if you look at the base here, okay, here we have sodium hydroxide, extra hydroxides being put in the water. Okay, every single molecule of NaOH will split into two parts, positive Na, negative OH. Okay, and that is what makes it strong, is the fact that every single molecule of NaOH will split up in water. Okay, if we look at the acid, same thing. Okay, here's your extra hydrogen. Okay, extra hydrogens make hydroniums, and that's what makes it an acid. Every single hydrochloric molecule splits apart into pieces. The difference is if you have a weak acid or a base, they only partially ionize. So for example, let's say we have hydrofluoric acid and this box represents a beaker. Okay, what that means is hydrofluoric acid, some of the molecules are going to stay stuck together like they're non-electrolytes, and then a couple of them will split apart. Okay, whereas with hydrochloric acid, every single one of these would have been split into positive, negative. For a weak acid or a weak base, there's only some partial ionization. So a few of the molecules might separate into charges. So that means it does conduct electricity, but it's very not good at it. Okay, it's a semiconductor. So if it would light a light bulb, it's only going to make a dim glow instead of a really bright one. Okay. So naming acids is really easy. Let's say you have hydrogen plus a non-metal. Okay, so for example, like HCl. Okay, the way that you name them is you call it hydro, and then we would name this chloride. If we were naming this like it was ionic, this is hydrogen chloride, but instead of saying hydrogen chloride, we call it hydrochloric. Okay, so hydro loses the end of its name, and instead of "ide," we use "ic." If we were naming HBr. Okay, so again, hydrogen plus one nonmetal. Okay, that's going to be hydro. And then instead of bromide, it's bromic acid. Another example, we have hydrogen plus one nonmetal. Okay, that's hydro. Instead of iodide, it's iodic acid. Okay, the other possibility is that hydrogen is stuck on a polyatomic instead. So, for example, NO3. Okay, this would be called hydrogen nitrate if we were naming it like an ionic bond, but we don't name it that way. If you have a polyatomic ion, you actually just drop the hydro completely. So the entire name is based on the nitrate. And in this case, we don't end the names the exact same way we would with an ionic bond. So ATEs get changed to IC, just like with the other naming. So this is called nitric acid. If we were looking at HClO3, okay, again, we don't need to worry about the hydrogen because that only is for when you have a regular nonmetal. So this is called chlorate, but we change it to chloric acid. If the polyatomic ion ends differently, so for example, this is NO2, which is not nitrate, this is called nitrite, okay, then we need to have some kind of way of distinguishing between NO3 and NO2. So instead of calling it nitrite, okay, we change ITEs to OUS. So this is nitrous acid. So nitric was NO3 because of the 8, and nitrous is an OUS instead of an ite at the end. Just do one more example. Okay, here we have polyatomic ion, so that means leave out the hydro. Okay, which I'm just going to look up the name. This is called, oops, I'm just jumping ahead. This is called chlorite. So if it ends in ITE, you change it to OUS, and this is chlorous acid. Naming bases there's no difference. This is called sodium hydroxide. This is called lithium hydroxide. This is called potassium hydroxide. There are no special naming rules for bases.